Good morning. So this is the seventh meeting of Classical Mechanics 1 at CMI. Welcome back. So I believe the previous lecture has just ended. So we shall wait for others to join us. I hope I am audible.
Yes, sir.
Okay, great. Yeah, so the first problem set has been marked, graded, and I believe they are available to you on Moodle. So you're welcome to go through your answer sheets. And one more announcement. Yes, please. Okay. This Thursday, I believe, is a holiday. So we do not have a class on Thursday. Ayudha Puja has announced for Thursday. And I'm also glad that you have submitted your second problem set. That too will be graded shortly. Based on some of the feedback, I would again suggest that you try to submit the answer sheets well in time. There can be difficulties in compressing files at the last minute or converting from one format to the other and so on. So please do these things in advance. We will not accept late submissions. Okay, we have 51 students present. While we wait, are there any questions? Okay, so last time we had, among other things, discussed some things about vector calculus, the concept of a field, a scalar field, which is simply a function on your space, a real valued function. And then we talked about vector fields, which are ways of an assignment of an arrow at each point of your space. So a vector field includes the velocity field of a flowing fluid or the electric field in the atmosphere. These are examples of vector fields. And then we introduced a derivative, which is the gradient. Could take the gradient of a scalar field and get a vector field. That's a special type of vector field. And we then went on to integration. We spoke about how you could perform a contour integral or a line integral of a vector field around a curve, along a curve, to get a number. And generally, this integral depends on the endpoints of that curve or contour. Sorry, it depends on the entire contour. But in the special case, when the vector field is a gradient of a scalar, then the line integral becomes independent of the curve and depends only on the endpoints. So that was a brief discussion of vector calculus. And we illustrated these line integrals by talking about the work done by a force field while transporting a particle along a trajectory. Yeah, I believe.
Excuse me, sir.
Yes, yes. Who is speaking?
Shubham Kumar.
Okay, please go ahead.
Sir, is there an intuitive explanation for why this integral only depends on the endpoints when the field is a gradient of some other field?
Yeah, I mean, it
I
goes
mean,
back.
intuitive.
Yes, yes. I mean, intuitive in different ways. So I'll mention one. I mean, just think in terms of ordinary calculus. If you're integrating dx, yeah, from x equal to 0 to x equal to 1, you know that the answer is simply, okay, dx is a very simple function. Let me say d of x squared, right? In other words, 2x dx. Suppose I'm integrating 2x dx from 0 to 1. Now, of course, you can evaluate the integral, but since you know that 2x dx is actually the derivative of x squared, okay, I believe that Satyendra has got his audio on.
Yeah, sorry.
Yeah, okay. Yeah, so going back to this, if you know that you're integrating a function which is the derivative of some other function, then by the fundamental theorem of calculus, you know that the value of the integral is given by the difference of the values of the antiderivative at the endpoints. It is really an extension of that. In one dimension, every function that you're integrating can be written as d of something else. So we don't think too much about this. But in higher dimensions, that's not the case. And so not every vector field is the gradient of a scalar, and only when it is the gradient of scalar can you express the answer as the difference of the values of the scalar at the two endpoints. Yeah, does that help at all, Shubham Kumar?
Yes, sir. Yes, sir. Thank you.
Okay, okay. We will talk about this once again when we discuss work. So this matter will come up again. Yeah. Okay, so now we have 61 minus 3, so 58 students present. Yeah, so perhaps we can begin today's discussion. Now, last time we also discussed a few things. Okay, there's a question or from somebody. Let me see what this is. Oh, yeah. So the calendar beyond you has not been configured properly. It shows only 30 days. Goodness.
He's nobody.
Okay, so Anek has suggested this. Okay, this calendar, the 31st day of October is up there. It's in the northwest corner where Punjab is located.
Sir,
But
Anek isn't actually a student.
He's nobody. He's
here.
not so.
Anek is, we don't know who Anek is, but it's a pseudonym of some kind. There is really no Anek who's actually a student of
Okay.
CMI.
So, oh, okay. So, Anek, would you please identify yourself? What is your actual name?
So he's left the meeting. We just consider him a manifestation of all of us.
Yeah, exactly. We can't trace Anek. It's actually amazing how discreet they are.
Okay, all right. Okay, Romit Roy Chowdhury said something, but okay. All right.
Was I not audible?
No, you were audible, but I didn't quite understand what you said. Please repeat yourself.
So I said he's left the meeting.
He has left the meeting. Okay, fine. All right. Let us now return to physics. Now, last time we also introduced some foundational concepts about time and the assumptions that go into non-relativistic classical mechanics. In particular, that we assume that the speed of light is infinite, and this is a good approximation as long as the speeds of particles or observers are small compared to the speed of light. So that is the approximation that we shall make henceforth until we talk about relativity later on. And within this framework, it is possible for all observers, all of us, to synchronize our clocks in such a way that we all agree upon the time of any event. And moreover, the simultaneity of two events is also something we can agree upon. We also agree upon the past and future of a given event. They are the same for all observers. Lengths of meter stakes, time interval between ticks of a clock are again all the same for all observers. Masses of particles are the same in different frames for different observers. And we also mentioned the principle of causality, which is a general principle, namely that cause precedes effect. And that simply says that you cannot send a signal from an event to an event that precedes it. So these were some basic assumptions that go into non-relativistic or Newtonian classical dynamics. Now, in this lecture, I intend to introduce some additional concepts. Most important among them, and the first among them, is that of degrees of freedom. So let me introduce this through an example. Suppose you have a point particle that is moving in three-dimensional space. We will say that this particle has 3 degrees of freedom. And this is because we need 3 coordinates. Suppose we use Cartesian variables, then we need x, y, and z coordinates of the particle at any instant of time. So to locate the particle at a given instant of time, we need 3 real numbers. And so we will say that the particle has 3 degrees of freedom. It is important to know, to realize that the number of degrees of freedom does not depend on the nature of forces or interactions and such like. It is a purely, if you like, a geometric concept. I mean, not geometric in a very deep way, but it has nothing to do with forces and interactions between particles and so on. So in particular, a free particle, that is one that is isolated, far away in outer space, not subject to any forces or interactions with other physical objects or fields, and a particle subject to Earth's gravity, moving in 3-dimensional space, both have 3 degrees of freedom. So it doesn't matter if the particle is under the influence of Earth's gravity or you have turned gravity off, the number of degrees of freedom does not change. So this is a very basic concept and a useful one. On the other hand, a bead that is constrained to move along a fixed wire. Yeah, so suppose this is my wire and I've attached a bead to it. And the wire passes through the bead and the bead is not allowed to spin. Okay, so we are supposing it can only be translated along the wire. Then that bead has precisely 1 degree of freedom, because all you need to say is at what distance down this wire it is located, and then you will know the instantaneous position of that particle. Similarly, if you have a wire that is not straight but bent, and a bead that is traveling on it, or an ant that is walking on it, again, not allowed to go round and round the wire and such things, then we will again say that this particle has 1 degree of freedom. Any question about this concept? Let me give a couple more examples. Suppose you have a particle that is constrained to move on a spherical surface. We'll call it a sphere. Yeah, a sphere is actually just the surface of the sphere. Sometimes we think of the whole solid sphere, then I will say solid sphere. But when I say sphere, I just mean a spherical surface. So suppose a particle is constrained to move on a spherical surface. An example would be the bob of a pendulum, for instance, that is rigidly attached to the end of a rod whose other end is fastened to a fixed support, a pivot. So this is an example. This is my pivot and this is my rod, and my bob is at this end. Now the pivot is held fixed, but this thing can rotate in any which way. So now we will say that the bob has 2 degrees of freedom because it's constrained to move on a sphere of fixed radius. Yeah, so that's an example of a system with 2 degrees of freedom. So here's the picture. This is my particle at the end of this bob, and it can travel on this sphere. Another example is if you have a particle moving on the Euclidean plane, it again has only 2 degrees of freedom, which can be taken as the x and y Cartesian coordinates.
Sir,
Yes.
so why 1 degree of freedom for that bead on the curved trajectory?
Yeah. So okay, Shakti Chauhan, yes. Okay, let's suppose that we designate one end of the wire as the origin, okay, for our convenience, and we define a coordinate which is the arc length along the wire. So this is 1 centimeter, 2 centimeter, 3 centimeter, 4 centimeters, 4.5 centimeters, and so on. Now to locate the bead, to specify where it is, all one needs to say is how far down the wire it is, at what arc length it is located. So it requires only one variable, namely the arc length. So arc length.
Sir, is there a more mathematical definition, like some dimension of some space or something like
Indeed.
that?
Correct. Yeah. So if the particle is free to move in 3-dimensional Euclidean space, then the number of degrees of freedom is simply the dimension of that space. So here it is moving on a curve, and the dimension of a curve is 1. It's moving on a plane, the dimension of the curve is 2. That's all. Is that okay?
Okay, so curves are, but curves are not linear space, right? Like a plane is a linear space, R3 is a linear space, but a curve is not a linear space.
Correct. Yeah. So this is not the dimension in the sense of linear algebra. It's a dimension in the sense of manifold theory. So it's a different concept of dimension. So that is why I avoided using that term. Rather, we can be very concrete. If I have a curve, there is a very concrete variable, namely the arc length, that can be used to parameterize the curve. And all you need to say is at what arc length the particle is located, at what distance from a chosen origin.
Okay, so thank you, sir.
Parameters to describe the motion, something.
Exactly. Yeah. How many free parameters do you need to describe the instantaneous location of the particle? Yeah. So I can write that down. Number of degrees of freedom is the number of parameters. And when I say parameters, I mean real parameters needed to specify its instantaneous location.
So if it's a rigid body, will it have 6 degrees of freedom?
You are quite right. A rigid body has 6 degrees of freedom. Sorry, who was asking that question? Rishinanda. Okay. Yeah. I will say more about that in a moment. Yeah.
Instead of location, shouldn't be state, like, because for rigid bodies we're also considering the 3 degrees of freedom has the rotation about XYZ axis, right? So shouldn't we say state instead of location?
No, the concept of state is a different concept. The concept I'm speaking of is not the state. The state includes the specification of where you are and where you're going. Whereas the location has less information. I'm only saying the bead is here. I'm not saying that the bead is moving this way or that way. Yeah. So if you want to specify that additional information or how fast you're moving this way or that way, then you would be specifying the state, and then you need more parameters. You need not just the arc length distance, but also your velocity at that instant of time. So it's a good question, and the terminology is carefully chosen. We are only specifying the location at this stage. We will talk about the state later on. Is that clarified, Siddhansha?
Yes, sir.
Yeah. Okay. So since sorry, who asked about the rigid body?
Sir, it was me.
Oh, Siddhansha. Okay. Yeah. So here's a rigid body. This is a bottle. Now let us ask how many degrees of freedom it has. Okay, let's select some kind of marked point in the rigid body. Let's say the cap. Yeah, let's think of that as a point. Now, to locate the rigid body, you first need to locate the cap. At least this is one way to do it. I mean, the cap could be anywhere in this room. So I will locate it here. And how many parameters are required to specify the location of the cap? Could you answer that?
So 3 points for the cap.
Exactly. You need the X, Y, and Z coordinates of the location of the cap. Yeah, I mean, think of the cap as very small. Now, having located the cap, you still need to, so the cap is now fixed. But given that location of the cap, the rigid body itself could be oriented in many different ways. And okay, there's nothing special about the cap. You could have chosen the center of mass of the rigid body or some other point in the rigid body. So now we can ask how many additional degrees of freedom the rigid body has once the location of the cap is fixed. So there is 1 degree, there are 2 more degrees of freedom because I can rotate this about just like I rotated my pencil, but there is also a 3rd degree of freedom because I can rotate the bottle about its axis as well. So there are 3 rotational degrees of freedom in addition to the 3 translational degrees of freedom that were needed to locate the cap itself. So we will say that the rigid body has 6 degrees of freedom. These are needed to specify its instantaneous location. And by location, I include the orientation, how it is pointing, yeah, which way the the lettering is pointing, and so on. And this is not the state. The state will include information about how fast it's rotating or how fast it's moving. That information I am not specifying at this stage. Is that okay about the rigid body?
Yes, sir.
Okay, so I will just write here a general rigid body has 6 degrees of freedom. 3 translational and 3 rotational. And that's what we just explained. So, yeah. Now,
so bead itself is a rigid body, so it should have 3 extra degrees.
Yeah, okay, so that's right. The thing is that I considered an idealized bead. I said that that bead is not allowed to spin. So you're supposed to think of the bead as a point particle. But you're quite right. If I allow the bead to spin, there will be 1 more degree of freedom associated to that rotation. Does that clarify the question you asked just now?
So why 1 shouldn't be 3 more?
Well, okay, it depends what kind of bead you have, but I mean, I'm thinking of this as a okay. I'm thinking of a rigid bead which is attached to this rod, yeah, and all it can do, it can move on the rod or you can spin it, yeah. There is no 2nd and 3rd rotational degree of freedom because the wire is fixed. The wire is fixed. The bead can only move along the wire or it can spin. So it will have 2 degrees of freedom. And if I take my idealized bead to be a point which cannot even spin, then even that spinning degree of freedom is lost and it has only 1 translational degree of freedom. Is that understandable?
Yes, sir.
Okay, great.
Also,
yes.
No, I don't think I understood the 3 rotational degrees of freedom for the bottle case. Could you explain that?
Yeah, for a rigid body. Yes. Let me explain that. Yeah. Okay. So here's my rigid body, this bottle. Now let's think about how I can. So I've already fixed the location of the cap. All right. I mean, think of the cap as a point, right? It's not extended. Okay. Now having fixed the location of the cap, I still have a lot of freedom in orienting the body in order to fix its location. All right. Yeah. Now let us count how many degrees of freedom there are for that. For instance, I can rotate the bottle.
Yeah, I understand.
Yeah, so that is 1 degree of freedom, because I need to tell the angle that this Bisleri sign makes with respect to some reference direction. All right, the angle. So that's 1 degree of freedom. So I rotate it to the orientation I wish to have about that axis. Now, in addition, I can orient the bottle in any which way I like, holding the cap fixed. All right. There are 2 degrees of freedom, because let us imagine the other end of the bottle, the bottom of the bottle, that can be any point on a sphere of distance of radius this much from the cap. Okay. So points on a sphere are specified by 2 coordinates.
Okay, right.
Yeah. And therefore, we have 1 sort of spinning degree of freedom and 2 degrees of freedom associated with the orientation on a sphere, the location of the other end on a sphere. So totally 3 rotational degrees of freedom.
Okay.
So which 2 parameters we can give to a location on a sphere?
I'm sorry, could you repeat your question, Shakti Chauhan?
Which 2 parameters we can define for a location on a sphere?
Okay. Which 2 parameters? Let's choose theta and phi, the 2 spherical polar coordinates that we introduced in the 5th lecture. Yeah, you can use them. Yeah. If you don't like spherical polar coordinates, you can use x and y. Yeah, because z is then fixed by the square root of r squared minus x squared minus y squared. Yeah, because it's a sphere of fixed radius. So you can choose 2 of your Cartesian coordinates as you wish. And then the third will be fixed. Of course, I mean, the Cartesian coordinate cannot be so large that it's outside the sphere. Yeah, but to some extent, you have 2 free parameters.
So if there wouldn't have been any sticker on the bottle, then it won't have the other.
Okay. Yeah, you're quite right. If the sticker was not there, but there's still water droplets. So I can still rotate those water droplets. Yes. So we are saying that different points on the bottle are truly different. They can be distinguished. And if there was no sticker, I will take a little paint and put it somewhere on the bottle. A very, very little bit of paint so that we can choose, we can specify and observe its orientation. So that's what we mean.
Sir, I had a question. Like, if degree of freedom is like, is degree of freedom like least number of parameters required to like specify its like location?
Yeah, it's not the least. I mean, it is the number of parameters. So you are quite right. The number of parameters, number of real parameters needed to specify its instantaneous location. Indeed.
Location plus orientation.
Sorry, Ruptak was speaking. Could you please tell me if that is okay?
Yes, sir. Yes, sir.
Yeah, I mean, it is the minimum number, but it's not like you can, if you try to give more, there will be a redundancy in them. They will be related to each other. They would be unnecessary.
So
we need location plus orientation as well, no? For the degree of freedom. Not only location.
Yes, Shakti John. Yes, we need both the location. I said the location of the cap. Yeah, the orientation of the rigid body includes the locations of all the points on the rigid body. All right. So it is just for our convenience that we are talking about some as orientational and some as location of the cap. At the end of the day, you need to locate all the particles in the rigid body, and that requires 6 parameters. We are only for convenience splitting them into 3 translational and 3 rotational. They all are required to locate the rigid body.
Sir, there can be rigid bodies which, like in 3D rigid bodies, which need less degrees of freedom, right? Which have less degrees of freedom.
You're quite right. That's why I said a general rigid body. That is, you're quite right. I mean, the rigid body is so thin that it doesn't have any spinning degree of freedom. You will lose 1 degree of freedom. You're quite right.
Okay.
Yeah. While we talk about rigid bodies, there are actually even simpler bodies or simpler systems. Okay, actually, there are some more questions in the chat box. Let me see. Akash Yadav. Why are we considering radius of sphere to be fixed while talking about the degree of freedom of a particle moving on a spherical surface? Well, your question has the answer to it. If the particle is constrained to move on a spherical surface, then its distance from the origin is fixed. And that is why we say the radius is fixed. Yeah. Okay, so Gautam Vishwanathan and Anand Balivada have also proposed such answers. Exactly. Yes, Akash has asked. So we are talking about a particle moving on a fixed spherical surface. Indeed, we are a particle moving on a fixed spherical surface. And at one instant of time, we look at this issue. Okay, any more questions? Yeah, let me come to in some ways, a different system. Suppose we consider 2-point particles, or rather 2-point masses, moving in 3-dimensional space. These 2-point particles move in 3-dimensional space. We will say that that system possesses 6 degrees of freedom. Yeah. So you need to locate the first particle by giving its Cartesian coordinates x1, y1, z1 for the first particle, first mass, as well as x2, y2, and z2 for the second mass. So as an example, you can consider the sun and the earth as point masses, because the size of the sun and the earth are rather small compared to the size of the solar system. Then the sun-earth system has 6 degrees of freedom. Right? It is important to bear in mind that this fact that it has 60 degrees of freedom is independent of what the force between the sun and the earth are. Okay, we just need 6 coordinates to locate the sun and the earth at any one instant of time. What is more, while talking about degrees of freedom, we do not restrict to any particular orbit of the earth around the sun. I mean, you may know that earth follows some orbit. That is irrelevant to counting the number of degrees of freedom. We simply ask how many coordinates are needed to specify all possible, let us say, initial locations of the sun and the earth. By initial, I mean at some instant of time that we call the initial time. Okay, so you are not restricting to a particular orbit, elliptical, circular, or in this plane, or all that stuff. Yeah. So is it clear why a 2-particle system has 6 degrees of freedom?
Hello, sir. This is Arjun.
Yes, please.
What is the reference point we are taking? Because depending on the reference, we can have different degrees of freedom.
No, that is not the case. No matter, okay, I don't know in which system you're talking about a reference point. Were you talking about the rigid body?
Yeah, if we consider.
Okay, no, it doesn't matter. No, you can choose any reference point. You can choose the bottom of the rigid body, a point at the bottom, or I just chose that cap. You can do the argument in the same way. You will get the number of degrees of freedom to be 6 once again. And similarly, for the particle moving on the bead or the particle moving on a wire, whether you choose your reference point at this end or that end doesn't really matter.
Sir, but the reference point should not move, right?
Oh, definitely. I mean, the reference point is fixed. Indeed, yeah.
Sir, so I mean,
the only thing that can move is the particle.
Yes, sir, so I mean, for the rigid body, a point on the body cannot be the reference point, right?
Okay, look, I mean, I think we are being a bit careless in the use of the word reference point. In the case of a particle moving on a wire, I used a reference point to define a notion of arc length. Right? That was the sense in which a reference point was used. Now, in the case of a rigid body, it is not in the same sense. Instead, what are we using? A reference point to locate the position of a chosen point in the body. So make a chosen point. That's not the reference point. The reference point is some origin. Let us be here. With respect to that origin and with respect to some Cartesian coordinate frame, the cap of the body is located at the coordinates 2, 3, 4. All right. So the reference point is still just over here. It's the origin. This is not the reference point. It is just a convenient point in the body, a convenient mass in the body that we are using to sort of discuss its location and orientation, whereas the original reference point is still fixed. And similarly, when I want to orient the body, to talk about theta and phi angles or the rotation about the axis, again, we need some reference direction. That is, I will say that the reference direction is such that when Bisleri points to my nose, the angle is 0. So my nose is then the reference point or the reference direction. It's not the point in the body. So we can talk about a marked point in the body or the center of mass of the body. They are not the reference points that we mean in the sense of the reference point at this end of the curve. Does that help at all?
Yes, sir.
That was Aryan Kusre, am I right?
Yes.
Oh.
Excuse me, sir. I have a question sort of related to that.
Yeah, so this is
Aryan's
Anand,
question.
Anand Balivada, is that right?
Yes, sir. Yes, sir.
Okay, please. Yeah.
What if we consider the sun to be, like in the sun-earth system, the origin, right? If the sun is the origin in that system, so rather than specifying 3 coordinates for the sun, if it was just 0, 0, 0, and you had the earth orbiting it, right? And
yeah,
if would you still consider there to be 6 degrees of freedom?
Oh, definitely, because to choose the location, see, you have to locate the origin at the center of the sun, all right? And there is a choice involved in that. And in fact, you have to fix 3 parameters to bring the origin to the center of the sun. So you've already, I mean, it's just like saying, if I want to choose the location of the cap as a kind of reference point in order to talk about the orientational degrees of freedom, then I've already located the cap somewhere and I've chosen those 3 coordinates already. So it's the same with the sun-earth system. If you already decided to locate the sun somewhere in your coordinate system, you made a choice of 3 coordinates. Is that clarify?
Okay, that clarifies, yeah, because this is the initial position, right? Because in practice, maybe the sun is like you can consider it fixed, right? Sort, at least to some degree.
No, I mean, it depends what you're talking about. You can always go to a frame where the sun is fixed. Yes, that is right.
Yeah.
But in order to locate the sun in the first place, with respect to some external origin, you still need 3 coordinates. And we must not forget that.
Okay, thank you, sir.
Yeah.
Sir?
Yes.
If these 2 point masses are moving in a particular straight line and we fix the reference points as that point line on that particular line, then there will be 5 degrees of freedom.
Well, okay, let me take your example a bit more carefully. Suppose we have a line, and we have 2 particles on that line. This line is fixed. Okay, this line is fixed. It's the x-axis. Now I need 2 coordinates, namely x1 and x2, to locate the 2 particles. That's it. The system has 2 degrees of freedom. Is that so? So that is a concrete example. Is that what you had in mind?
No, sir. In this example, the sun and earth example, you pointed out that if 2 point masses are moving in 3-dimensional space, have 6 degrees of freedom. So suppose in a particular case, they are moving on in a straight line in the 3D space.
Okay.
And if we take the reference point on that particular line on which they are moving, so then we will have the 3 degrees of freedom for choosing the reference point and 2 degrees of freedom for specifying the location from on that straight line.
Okay, I'm sorry. The statement that you're given is a little bit unclear to me. I don't know what it means for the sun and the earth. When you say the sun and the earth are moving on a straight line,
no, I'm not saying about sun and earth. I'm saying if these 2 points are moving in a 3D space, and if in a particular example, suppose they're moving in a straight line, and if we take the reference point on that particular line.
Wait, before you go further, see, when you say they're moving in 3-dimensional space, that statement already says there are 6 degrees of freedom. There may be a particular trajectory when they happen to move in a straight line. That is irrelevant to the number of degrees of freedom. That is like saying the sun and the earth in this realization are in an elliptical trajectory around each other. That's a different matter. So I would not like to confuse a particular type of motion or a particular trajectory, a particular orbit with all possible initial locations of my system. These are different concepts altogether.
Sir, what I think he's trying to say is that if we consider the reference point on the line joining the sun and the moon, like we consider it a rod, and then we our representative point of the rigid sun Earth motion. This is on that line.
I just want to clarify: the sun and the moon are being considered as point particles. We don't need any reference point inside the sun or the Earth.
Yes, sir. Sir, what I mean to say is we consider that system as a body, and we have a representative. We choose a point to like origin in a rigid body, right? A reference point in a rigid body.
Wait. I mean, we're getting a bit confused here. I'm sorry. Wait. If we consider the Sun-Earth system, these are 2 point masses moving in 3-dimensional space. Let me draw that 3-dimensional space here. We have chosen an origin for that 3-dimensional space completely arbitrarily. It has no relevance to the number of degrees of freedom. I have the sun here and the Earth here. To specify the location of the sun, I need 3 coordinates, X, Y, Z. And for the Earth, I need capital X, capital Y, and capital Z. 6 degrees of freedom. And the number of degrees of freedom does not change if I relocate the origin of my coordinate system. It's still some X prime, Y prime, Z prime, and capital X prime, capital Y prime, capital Z prime. Yeah.
Sir, I'll try to articulate it better, and then I'll send it in the chat.
Perhaps that would be better. Yeah.
I think they mean to ask if we are taking sun and earth as one body, like a rod with masses concentrated at the ends alone. Can we say that it has only degrees of freedom?
But then they are not
let
free
me take
to
that
move.
up. They are not free to move, and let me take that up. Yes, you are free to think of the Sun-Earth system as 2 masses at the end of a rod, except that this rod can get elongated and shrunk. All right. Now you still so you will still need 6 coordinates. One to locate the middle of the rod or something, and then the vibrational mode of the rod as well.
Can you please clarify this statement, moving in 3-dimensional space? I didn't understand what this means.
When I say something is moving in 3-dimensional space, I mean, for instance, a fly flying in this room. That's an example of a particle moving in 3-dimensional space.
But if that fly is flying in a straight line, would you say that it is still moving in 3-dimensional space or in a 1-dimensional space?
See, there is a difference between a fly that happens to be flying along a straight line in one realization, but flies are not always traveling along straight lines.
No, I'm just taking a particular case. If like suppose if we take that particular case.
Oh, sure. Then you are saying then it's not a fly flying in 3 dimensions. It's a fly moving on a straight line, and then it has only 1 degree of freedom.
That's what I'm saying, that if 2 masses are moving in a straight line in a 3-dimensional space, and if we somehow get to that straight line by choosing 3 coordinates, then there will be 3 degrees of freedom and 2 for the specifying the length of those particles on that particular line.
No, I'm sorry. You really need to rethink what you are saying. When we talk about 2 particles moving on a line, they have 2 degrees of freedom. You just have a line. The fact that this line lies in 3 dimensions is irrelevant to the question at hand.
Suppose our initial reference is like, let's say, on Earth.
Excuse me. Wait, Shakti. See, this can get very confusing if we don't specify our system clearly. Yeah. We must not talk about reference locations before we talk about the system. What is the system you wish to define or describe? Please don't go into the question of reference locations before talking about your system. Suppose your system is one where 2 masses are on a line. Yeah, that there is no need for any reference point and all to define your system. This system has 2 degrees of freedom. The 2 particles can move on a line. Each of them has 1 degree of freedom. That is all. I encourage you to please think about this once more, and maybe you can reformulate your question more carefully if you still have a confusion about this. I mean, do you have some urgent question about this right now?
Sorry, sir. I mean, I'm not comfortable with this. Like, I need to think about this.
Yes, I think so. Yes, I think that's a good idea. If you spend some time, please look at the examples that I have brought up. That would hopefully clarify things. And then please think for yourself what system you are describing. When you say 2 bodies moving on a straight line, then is that straight line fixed or is it not fixed? You have to be very clear about what system you are considering, and then we can identify the number of degrees of freedom.
Sir,
yes.
I had a related question.
Who is speaking? Yeah.
This is Gautam, sir.
Yeah. Yes, please.
So suppose we have 2 point masses, maybe the sun and the earth. So we'll take three coordinates to specify the location of the sun. Now,
yes.
Suppose that we know somehow that the other point mass is for certain exhibiting uniform circular motion around the other point mass. Suppose we know that for certain somehow. Then would we still need 3 coordinates to specify the location of the second point mass, or can we reduce it to 2?
Look, we have given a very clear definition. The concept of number of degrees of freedom is totally independent of any particular trajectory, type of force, nature of motion. All that is irrelevant. The number of degrees of freedom is the number of coordinates required to specify an instantaneous location of your system. If you have reduced the motion to a particular type of motion and are wishing not to consider the remaining possibilities, then you have to talk about your new system. Yeah, so then we have to talk about a new system. You're talking about planar motion of the earth around the sun. Yeah, that's an excellent system to consider. Planar motion of the earth around the sun has a totally different number of degrees of freedom. The sun has to be located with 2 degrees of freedom, some point on the plane, and then the earth has to be located on that plane, so 2 more degrees of freedom. The system has 4 degrees of freedom. Now, how you came to this planar system is a different question. Yeah, I mean, you may have some knowledge that the motion is on a plane. You have provided additional knowledge and simply changed your system. So it is a different question.
That makes sense, sir. Yeah, thank you.
Yeah, you're welcome. Okay, so there is no doubt that this concept is not a totally straightforward concept, and I'm very happy that you have asked so many questions. Perhaps there are more coming. So, yeah, sorry, who was asking?
So we can say that number of degrees of freedom doesn't depend on our reference, but will depend on our, like if we are describing our motion in 3D or 2D.
See, let's put it this way. The number of degrees of freedom does not depend on any reference location, origin, and all that. Those don't affect the number of degrees of freedom. What they do affect is the manner in which you will specify the coordinates, right? What is the value of x at this location? To give that value, you will need some origin for x. Yeah? So it enters only that way. But the fact that you need 3 variables, x, y, and z, is independent of the choice of origin.
Okay, so it depends on the way we choose to describe something, but it does not depend once.
See, it depends. The origin only helps to give the numerical values of the coordinates. Yeah, or to use spherical polar coordinates as opposed to Cartesian coordinates and so on. It does not affect the number of degrees of freedom. If you use r, theta, and phi, you still need 3 coordinates. If you use x, y, z, you still need 3 coordinates. So that number is independent.
If we take sun and earth, and we start over without any knowledge of how its motion is elliptical, and we go through solving it, we have 3 degrees of freedom.
Wait, the concept of a solution is a much deeper concept. We have not solved any equation at this stage. We are simply locating the bodies. That's all at one instant of time.
Yes, sir. What I'm saying is, if we start out with a plane, then we have 2. Like if our description itself is starting with a plane instead of 3 dimensions.
Correct. Yeah, we are talking, we decide to talk about 2 bodies moving on a plane. All right. In that case, there are only 4 degrees of freedom. 2 to locate the first body, 2 to locate the second body. Yeah, and this is before solving any equations of motion. Is that clear, Rishi Nanda?
So I'll just repeat what you said, sir. So,
sir.
Wait, Shakti Chan, I'm still answering Vishinanda's question. You wanted me to repeat what I said?
No, sir. I will repeat. You see if it was if I got it.
Okay. Please go ahead.
If we choose to start out describing our whatever we're describing in 2 dimensions, then we have 4 degrees of freedom.
Yes.
Or 2 bodies. the same thing if we start out on 3 dimension and later realize that it is some trajectory which can be described on 2 dimensions, we still haven't had 6 degrees of freedom.
Okay, let me try to clarify that. The Sun-Earth system really has 6 degrees of freedom. The fact that the motion, because you've observed things or have decided you've sought to solve equations, are all coming later. Now, let me take up this issue in more detail. Look, which plane does the motion happen on? Yeah, you don't know that. The motion, that the plane on which the motion happens is itself to be determined. It could be this plane, it could be this plane, this plane, this plane. Yeah. So the number of degrees of freedom includes that of the specification of the plane on which the motion happens. All right. And that's where the remaining 2 degrees of freedom. To orient a plane, you need 2 more degrees of freedom, namely the direction of the normal vector to the plane. So the 4 degrees of freedom that we counted for 2 particles moving on a plane have to be augmented by the choice of the plane itself in order to correspond to the full 6 degree of freedom Sun-Earth system as a whole. Does that help?
Yes, sir. So if we
so just one moment. And initial conditions will determine which plane that motion is happening on, right? So you do need to specify that plane. Please go ahead.
So if in paper we are drawing a circle and describing it in 2 dimensions,
yes,
we are restricted. I mean, there is still the other 2 dimensions, I mean, other 2 degrees of freedom attached to it, which we will
have forgotten about by drawing a plane.
Yes.
and I can't emphasize this enough. The concept of degrees of freedom is a very, very fundamental concept that comes much before the concept of a trajectory. So if you talk about a trajectory, you've already gone too far. When you talk about the degrees of freedom, it has nothing whatsoever to do with the trajectory, elliptic, circular, on this plane or that plane. Nothing of that sort. Degrees of freedom are simply locating particles. No mind what the forces are at all. Okay, it has nothing to do with forces, nothing to do with trajectories. Yeah. Okay. Any other question?
One thing just, oh, sorry. Go ahead.
Oh, I'm sorry. There is another question from Ankit Gayan who asks, so changing our system changes the degrees of freedom of particle moving in that system? Of course, the number of degrees of freedom depends on your system. You change your system, in general, the number of degrees of freedom will change. What was the next question?
Yes, sir. Like 2 points in a given system can't have different degrees of freedom, right?
See, the specification of the system includes telling what the particles in the system are. So okay. when you say 2 particles in a system, that's it. You have specified your system. I mean, you have to say where they're moving, of course.
Okay.
Okay. So
understood. Thank you.
Satya Srivani. Yeah. Okay. Any other question?
Yes, sir. What I've understood is that we also need to specify sort of what, I guess, dimensions the particle is allowed to move in when we're specifying the system itself.
Indeed. Yeah.
Okay.
Yeah. I mean, it's different talking about a particle moving on this table and a particle moving in this room. They're totally different systems. We need to say that. Yeah.
Okay. In that case, I did have one extension of this question also. What else do we have to specify for a system? So we have to specify the location, orientations also, and dimensions. Is there anything else?
No, all we need to do is locate all the particles in my system. That's it. Concept of orientation is a convenience to adjust certain things. Yeah, after all, finally, I have to locate all the particles in this mobile phone. I can call some of those locations as orientational locations and some of those as translational locations. That is purely a convenience. At the end of the day, I just need to fix the locations of all the particles.
Okay, sir. Okay.
Yeah.
Got it. Thanks.
Good. Okay. So if there are no further questions on this important concept of degrees of freedom, I shall proceed. Okay, there is another question from Rishabh Gupta. Since the rigid body has 6 degrees of freedom, if we give coordinates of 2 points on the body, then it uniquely satisfies one location of a rigid body. Is it correct? Yes, yeah. I mean, essentially that is correct. Yeah, yeah. So yes, you're quite right. Let me choose these 2 points. For instance, I'll choose the points to be the cap. So I give the coordinates to the cap. Yeah, let it be 1, 2, 4, and then I choose to give the coordinates of the B in Bisleri. All right, maybe that is 5, 6, 7, and then that completely fixes the location of the bottle. I mean, I can't then rotate the bottle or shift it this way or move it that way and so on. All right, is that clear, Rishabh?
Yes, sir.
Okay, great. Any more questions? I am truly impressed by your thinking on this matter, all of you. Okay, so let's go to a system with somewhat more degrees of freedom, number of degrees of freedom. A fluid consisting of, say, 10 to the power of 24 molecules in a bucket has clearly a very large number of degrees of freedom. Yeah, so we can take them to be the 3n Cartesian coordinates needed to specify the instantaneous locations of each of the n molecules treated as point masses. Okay, so if you have n molecules, we have 3n degrees of freedom. Yeah, I mean, treating these molecules as point masses. Okay, so that's another example at another extreme. I mean, yeah, we've talked about point particles, a single point particle or maybe 2 of them. That's 1 degree of complexity. Then we've got a rigid body that's 1 step higher. And now we're talking about a system with an exponentially large number of degrees of freedom. These are all interesting, and they sort of branch into different areas of mechanics. Okay, any question about this thing about the gas or fluid? Okay, now we will. Yes.
First, we need to locate the bucket now.
Oh, no, the bucket is fixed. The bucket is fixed. So we have fixed the bucket. The bucket is my bottle. It is fixed here, and the fluid is the one inside the bottle. I'm not moving the bucket. So we need to be very clear about our system. The gas in this room, so that fixes where the room is located, where the gas is located. I mean, I can't move the room elsewhere. That's a different system.
Oh, sir, yeah. I mean, there is a question that I have, but like about the fluid or the gas, right? And specifying the initial positions of all the molecules in either the fluid or the gas, right?
Yes.
I mean, is it actually like, legal to do that, considering that like the motion of everything is random in some sense, right? In a fluid or the gas. So if at any point,
excuse me. No. Okay, see, when you say the motion is random, you have already made some judgment about the nature of forces and what's happening. You're telling me that this is at finite temperature, there is some thermal motion, all that. That is all irrelevant. If I have a bunch of molecules in a room, it has 3n degrees of freedom. Yeah, this is independent of the nature of the motion.
Okay, yeah, that makes sense.
Like the nature of the forces. Yeah, see, and I should also clarify that in Newtonian mechanics, see, it is not really true that the motion of the molecules in the gas or the gas itself is totally random, as you say. One has to be very careful as when we use such a term, and perhaps that discussion has to happen elsewhere. I mean, there is just like 2 bodies can move in the Sun-Earth system. in a particularly regular way. You can have 4 bodies moving in a particularly regular way, or in a determined way. If you give the initial conditions and we know the forces between them, then Newton's laws tell you how they move. There is nothing random about it. Randomness arises when you decide that you are a bit tired and don't want to pay attention to certain things, and then you ignore certain other things as well. Then things look random. Or you simply have no capacity to track the motion of 10 to the 24 molecules, and you instead focus on some macroscopic variables like the pressure they exert, or their energy or their temperature. Then you will be approximating the motion in a certain manner, which you may describe as somewhat random. The motion of these particles, as described by Newtonian mechanics, is not random at all. One needs to be more careful as to how this supposed randomness arises and what one means by that randomness. There are different aspects to that.
I have to add something, sir. Can we say that degree of freedom is the number of ways we can execute potential energy in form of kinetic energy?
No, definitely not. No. I would not like to think about, see, as I said, the concept of number of degrees of freedom is a primitive concept. It comes before forces, comes before energies, it comes before potential energy, it comes before kinetic energy. You don't need any concept of kinetic or potential energy to define the number of degrees of freedom. I would caution against using any such concept here.
By freedom, we means the freedom of motion. No, or
correct. Correct.
So motion.
Well, the freedom to locate it is the degree of freedom. That's all. I can locate this point mass here or there if it can move in this room. That's all we are saying. How fast it moves, what the potential energy in this room are all beside the point. There are further details that are used to describe the dynamics. Okay, I have a question from Ishan Verma. In this fluid motion example, are we considering one of these particles as the origin? No, definitely not. There is no need for any origin to count the number of degrees of freedom. If no, we would require to specify one more point, right? No. See, I have 2 particles. See, a gas with n particles is not very different from the Sun-Earth system. It's just that the number of particles is a bit more. So please don't confuse it that way. The Sun-Earth system has 6 degrees of freedom simply because you need 3 to locate the Sun and 3 to locate the Earth. And if you have 100 molecules, you need 300 coordinates. And you can have a fixed origin for your Cartesian coordinate system that is not associated to any of these point masses. That is simply some extra thing that is fixed for your convenience. If you change that origin, the number of degrees of freedom does not change. Okay, so Ishan Verma says, understood, sir. So that's excellent. Yeah, but thanks for your question. Okay, so okay, if there are no further questions on this concept of degrees of freedom, so I've tried to be very careful with this notion of degrees of freedom. And I would encourage you also to be very careful in your thinking. What we have discussed now will be very helpful to you when if you are a bit confused about it. So please do come back to it. And it is very easy to get confused about this, and you are not alone. Okay, so just a definition now of the concept of a configuration. What I've been talking about as a location in physics, in mechanics, is often called a configuration. So we will say that an instantaneous configuration of a system of 2 point particles is any possible location of the 2 particles. So this is one configuration, that's another configuration, this is another configuration. So if you've located both the particles, you have fixed the configuration. So configuration is the technical term used to describe the location of all the particles in the system. Okay. Yeah. Now I am okay. We still have a little bit of time, so I will now proceed to. Any question about this term configuration? Okay. I mean, we will use it now and then, and you will get more used to it, I think. Now, I wish to come to some additional concepts, the first of which I will call the zeroth law of classical mechanics. And this is the way I would like to phrase it. Now, the path followed by a particle in time is called its trajectory. Okay, so this is a notion we have introduced previously. The path of a particle as time flows is called its trajectory. So that trajectory is a directed curve in the space in which the particle is moving. Yeah, so it is a curve parameterized by time and directed towards increasing time. So that is our trajectory. Now, there is a very basic assumption in Newtonian mechanics that is often not stated, but I will just say it explicitly here so that we are aware of it. And I will call it the zeroth law of mechanics. The zeroth law of mechanics can be regarded as saying that the trajectory r of t of a particle is a twice differentiable function of time. Okay. So this is a basic assumption that is going into mechanics, Newtonian mechanics. It is worth noting what a law of physics is. In a somewhat lighter but serious vein also. I would like to think of a law of physics as something that is not a self-evident fact. All right, it is something that has to be deduced from observing nature, doing experiments. Okay? It's not some self-evident fact. It is not something that we can just play with sentences and words and concoct some statement which is always true. That would not be considered as a useful law of physics. Okay? In particular, more often than not, most laws of physics can be violated. They are valid in a certain situation or in certain class of situations, but there are probably places where they simply are not valid. Okay? So we have to be clear about that. Laws of physics are not inviolable. They are valid usually in some approximation or when you ignore certain effects. Yeah. So we have to be used to that and accepting of that. In particular, this zeroth law of mechanics, I mean, I'm not going to go so far as to say that all laws of physics can be violated. I'm not going to go so far, but they usually have their regime of validity, and we should be very much acutely aware of that. Okay, so now, for instance, this zeroth law of mechanics, which I have stated, and which requires that we are considering a system where the trajectory is a twice differentiable function of time. Unfortunately, it doesn't hold for all systems. It does hold for a vast majority of the systems we study. It is found to apply, for instance, to the motion of planets. Yeah, if you make a chart and watch the motion of a planet, the curve that it traverses is, to reasonable approximation, modeled as a twice differentiable curve. Twice differential function of time, the r of t. So it applies to planets. It applies to pendulum bobs, yeah, the motion of pendulum bobs. It applies to tennis balls or golf balls, cricket balls, the motion of those. Yeah, but there are contexts where it fails. For instance, it fails for Brownian motion, namely the motion of pollen grains in water. The trajectory of a pollen grain in water cannot in any useful way be modeled as a twice differentiable function of time. Yeah, so yes, in this particular case, it is a fact that this pollen grain is being knocked by water molecules very, very frequently, and so its path is very jagged. So the pollen grains in water are observed to follow very jagged paths, and it is simply not useful to model such a path as a twice differentiable function of time. That's not a useful approach. So Anand Bansal asks, this law is not valid if we consider any external disturbance like any impulsive force, right? Yes, in a sense. See, ballistic motion can be modeled by this. I mean, a particle moving in a straight line, the straight line is still very much a twice differentiable curve. So that's fine. And then after some time, if it gets kicked by an impulsive force and changes its direction abruptly, then at that point, the trajectory fails to be differentiable or twice differentiable. So indeed, when there are such kicks or some impulsive forces, this law fails to hold. But it's a little more than that. See, if it is that these kicks are very infrequent, then at least for significant durations of time, you can model it by a twice differentiable function of time. The problem arises when these kicks are so frequent that it's pointless thinking of those little short intervals of time where the particle happened to move in a straight line. They are not the main physical feature. So I hope Anand Bansal, the matter is clarified. Okay, so he says, got it. Yeah.
Sir, I also have a quick question about this. You said that it isn't useful to model Brownian motion as, let's say, any twice differentiable, path, right? But
Very
technically,
right,
if you
very
had
right.
like enough patience, like you said earlier.
No, I had to be very clear. We are in the business of modeling systems in effective ways. And the question is one of utility, helpfulness, and doing things in a time that and in a way that will be useful to us. So it is simply not practical or useful to look at those short instants of time, short durations of time where the pollen grain happened to move in a straight line. Simply following those, you cannot get much of the interesting physics of the diffusive behavior of pollen grains. There is a lot of physics in pollen grains which people, culminating the work of Einstein, understood, and that cannot be understood by focusing on only those times where it happened to travel in a straight line. That is not useful. So yes, my words are carefully chosen. It is not useful. You can do it, but you won't get very far.
Okay, thank you, sir.
Yeah. So, but that is a very good point you have raised. The word usefulness is a key word in this thing. We are in the business of making progress in understanding nature. If we don't do that, it's not useful.
Sir?
Yeah. Shubham Kumar, yes.
Yes, sir. But like, even if it's not useful, but like, how can we say that the law is not found to apply there? I mean, the law is still there. It's just not useful.
Correct. Okay. See, look. All right. This may become a matter of semantics. See, the question is whether there is a significant part of the motion that can be modeled. I mean, the words are very important here. Significant part of the motion that can be modeled as a twice differentiable curve. If there is, then this law is valid, and then we can work further, build a foundation on this law, and make further assumptions or deductions. Yeah, it is true that between two collisions with water molecules, the path is relatively straight and differentiable. But a lot of the physics is not there. A lot of the physics is in the collisions. So unfortunately, using this law in that system does not lead to an understanding of that system or making predictions that you can then check about the gross behavior of such a Brownian system. Is that helpful, Shubham Kumar?
Yes, sir.
Okay. Okay. Yeah. Okay. I don't know how convinced you are, but you are free to ask it again. Yeah.
So this law is more like use classical mechanics. If this is there, don't come to classical mechanics if this is not there.
Exactly. Yeah. There may be some other kind of mechanics called Brownian mechanics or some stochastic mechanics which will be more useful for studying such systems. Exactly. Yeah.
So it's more like a preamble for classical mechanics than physical. Is it?
Okay, see, I don't know. See, this is a law. Laws are assumptions. They are postulates. They are axioms. They are things that go in the preamble. Yes, these are all synonyms in the sense that I'm using them. If this doesn't hold for the system you wish to study, then that system will not be treated in this framework. You need some other framework. Yeah. Okay. Yeah. So I was saying this. Okay. Maybe what you're saying is that the word law is not such a good term to be used here. We can say this is the 0th assumption of classical mechanics, and then we will call Newton's first law the first assumption of classical mechanics, and so on. Yeah. So okay, that I'm willing to grant that a better word may be chosen. It's just that these assumptions, which are often called laws, are valid in a wide variety of systems, but they fail in other systems, and we must be fully aware of that, so that we don't go and try to apply it there and reach some pathological conclusion or some erroneous conclusion and then wonder what's happening. Okay, so in fact, there are other places also where this does not apply. For instance, and this is not so evident, it's a bit harder to understand. This law or this assumption fails for electrons in an atom. And they require a quite different kind of treatment, which is called quantum mechanics, which you will study elsewhere. And the point is that an attempt to describe the trajectory of an electron is fraught with difficulties, and one realized that a different approach is needed. And there was, it took a long time to understand that, but with the benefit of hindsight, we can simply say that it fails for electrons in an atom, just like it fails for pollen grains in water. Understanding how it fails and so on requires additional study. My intention here is to simply point out the limitations of Newtonian mechanics. It appears to be good in certain places. Beware if you apply it elsewhere. Okay, so yeah, so Isaac Newton formulated 3 laws of classical mechanics in his Principia in 1687, which was published in 1687. I mean, it was the culmination of the work of several scientists who preceded him. In fact, Newton said that he's standing on the shoulders of giants. I'm paraphrasing. But he did take an enormous step in formulating the assumptions and their consequences insofar as mechanics is concerned. Okay, so any other question about this concept, either that of degrees of freedom or this assumption of particles' trajectory being sufficiently differentiable in order to do the things we will do? Okay, so I have to stop at 1:10, I think. Yeah, I think that is the 1:05, is it? I'm sorry. So I'm already out of time. Okay, so just a couple of announcements. The first problem set has been graded, and you can see your answer sheets in Moodle. And the second thing is that this Thursday, there is no class on account of holiday. So our next lecture will be next Tuesday at 11:50 p.m. Any other questions right now?
Yes, sir.
Yes, Shubham Kumar.
Can we ask you questions on email? Gmail, whatever mail.
Yes, you may.
Questions.
Yeah, you can. Yeah, you may send queries that way. Yeah, of course, you are welcome to ask them in the class. That is also an excellent way, because then others can also benefit. But yes, additional questions you can ask. Yeah, of course, I have limitations as to how much I can answer. Yeah, I must also say that I have limitations as to how many emails and questions I can answer. But we shall make an attempt. And you're also, especially about the homework or the assignments, you're also welcome to ask TAs if you have specific questions about the grading. I hope that will not be the case. Yeah, but if you have questions about any problems in the homework, you're welcome to ask that as well. Yes, please go ahead.
Nothing, sir. I was like
Yeah.
telling, like I had a doubt, but I'm not able to frame it properly. So I could mail you after I have framed that question.
Yeah, that's possible. Yes, that's a good idea. Yeah. Okay. So any other questions at this point? If not, we will end this meeting and have a good lunch. I will be in touch with you about other course matters. Okay, have a good afternoon.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Enjoy your life.
Thank you so much.
Thank you.
Thank you, sir.
Thank you. Thank you.
Thank you, sir.
Yeah, you're welcome.
Thank you, sir.